branch predictions, it will take into account the last m branches outcomes, where those m branches is for preferably have last k bits same. Here the k bits what I'm mentioning is about the program counter bits. So it will try to store the outcome of the last m branches, and thereby it is trying to do. So it is something like a local table, local, because right, because it is maintaining some last m branches only. But when you just go with the tournament branch predictions, it's something like a global. I mean, what is it? Global branch predictors. Wherein right, it will try to retain the outcome of last m branches, irrespective of the program counter k bits. So it will try to retain the outcome of last last m branches. Okay. So for that, few components are essential, and on the day I have described what are all the components. What is that? So when you just go with those two topics, preferably right. You may get a problem and they will ask you to find out the, I mean, when you go with compiler, they will ask you to find out the number of stalls or how many cycles, total cycles it has been happened. So like that. And with respect to the prediction case, branch prediction case, they ask you to calculate the prediction rate. Okay. So misprediction rate, they may ask you to calculate. So you must be in a position to calculate that. So, I mean, that's it with respect to the first two topics. So today, right, we will go move on to the third topic, wherein, right, the same thing here, we are trying to exploit the instruction level parallelisms by means of hardware. Okay, so I told you two things. One is by hardware, another one is by software. By software is nothing but the compiler. This is by means of hardware. So today we are going to look onto the technique wherein how to exploit the instruction level parallelism using hardware. So first I will go with some PPTs. And regarding today's test, you kindly go through all the problems, all the examples that have been there in that unit one. Okay, so even you can think that I have just released the question also. So all the problems that are there in the unit one, I told you just to try to memorize the what is that formulas I told you. So based on that, you will get the questions today. So try to attend those questions, and don't think that similar kind of things will get it for your second CA or the third CA, whatever it is. Definitely you won't get it. So this time, right, you got this. Next time you won't get such kind of questions. But try to, I mean, 2 to 3 your exams is scheduled. Today 2 to 3 your exam is scheduled. So try to finish it up. I think 10 questions, not 10 questions, around 16 questions, 20 points. So 20 marks. You need to write the test for 20 marks. Fully it is all the questions. I just now I looked onto that. It's a problems. I mean, like what the exercise sample problems that is there in our textbook, right? Similar kind of problems. Maybe they may change the value. I haven't looked into the question also, but I just checked. I mean, what type of thing they asked. So kindly just look onto the formulas and accordingly you try to work it out. Okay. Okay. Hope is it visible, right? Is it visible?
Yes, ma'am.
Okay, so today's class, right, we will see how to do this with the help of dynamic scheduling. So which means we are going to use the hardware approach. So with the help of hardware, how to do the data scheduling. Okay, and above that they have given overcoming data hazards. So on the day when I mean in the introductory of what is that ILP, what are all the three hazards that is there with respect to data hazards?
True dependency, name dependency.
Okay, those those
Yeah.
yeah, rare, right? What are they? Var,
Ra, Va.
yeah, Ra, right? Read after right. WAR and WAW. Okay, right? Those are all the data hazards. So I told you earlier, right? Because we have three hazards. One is the raw hazards, then war and wow hazards. This is completely true data dependence, isn't it? So only, I mean, it is output of the previous instruction is given as an input to this. But when you go with these two things, it is not the case, right? One is going to be anti-dependence, and this is anti-dependence, and this is going to be output dependence. Okay, I think I gave a solution to this also. So what is that solution for anti-dependence and output dependence?
Renaming of register.
Yes. What is the solution?
Register renaming.
Yeah, isn't it? Register renaming. So that's what we are going to do it here. So here, I mean, we are trying to avoid this hazards, war and wow hazards. We have to go for register renaming. So this one we are going to see Damaslo's algorithm. Okay, this algorithm is all about these things. How to do this? Okay, so first we are going to see about what is the, I mean, need for dynamic scheduling, like what might be the problem with the compiler techniques, and what is out of order executions, and how using Damaslo's algorithm, how we are going to avoid this hazards, that is war and the wow hazards, because raw can't be done. Raw we cannot do it because if it is going to be dependent, output of that is going as an input to this, so it cannot be done. So only right we need to eliminate these two things. So I mean this algorithm is also focusing on this, how to eliminate these two hazards. Okay. So for that, right, we'll see how this algorithm is going to work and how the hardware structure or architecture of Damaslo's algorithm. Okay. So when you what is dynamic scheduling? So what we are going to do is in dynamic scheduling also the hardware is going to rearrange the instruction execution. Thereby, it is going to reduce the stalls. Here also the similar. Okay, it is also trying to rearrange the instructions, and thereby it is trying to reduce the stalls. And when it is rearranging the instructions, as we did for the compiler, it should maintain the data flow and also the exception behavior. It has to be handled properly. So that is very important for any cases. It is for whether it may be a static scheduling like compiler or for dynamic scheduling like hardware. It is going to rearrange, thereby it is reducing the stall. At the same time, it will maintain the data flow and the exception behavior. Okay, so what is the advantage when compared to compiler? It's a static scheduling. So how would what might be the advantage? Okay, first one is right. It enables handling some cases when dependencies are unknown at compile time. So you know about compiler, right? We doesn't know what is the value it is going to take. So probably right, if something is value oriented, we don't know that. Okay, so but this can be resolved during this dynamic schedulings. Okay, so something which you do not know at compile time, but it may know at runtime. So those kind of cases can be handled at runtime. Okay, so say so for example, just for an example, I'm giving. Suppose you have A of I something like this. Suppose we have A of J. Maybe right during runtime, I and J may have the same value, which may not be known during the compile time, but it may be known during the runtime. Okay, so such kind of things can be handled in dynamic schedulings. Other one is it allows the code compiled with one pipeline to run efficiently on different pipelines. So maybe right when you just if you take a compiler, the compiler will produce the output for a specific processor architecture. So it means generally it may give like this, but so when it is gives for every architecture, it has to do accordingly. That is the role of the compiler, right? Whatever the architecture we have for that architecture, the compiler has to produce it. But if if the hardware itself is going to take care of that, so what is need? I mean, that understood or not? So I mean, we can able to run the same code efficiently on multiple platforms. That's the thing. So since the hardware itself is going to schedule it, so irrespective of the things, automatically it can be done. But when you just go with the compiler case, compiler now, okay, this kind of architecture we have, only for that architecture it will do it. So assume that compiler will it keeps in mind as one pipeline, it will produce the code like this. But in hardware aspects, it may be parallelized, so that thing will be taken care at the hardware side. So that is the second advantage. And third thing is this allow the processor to tolerate unpredictable delays. Unpredictable delay is during runtime only we will get to know. Suppose, right, if the data is going to depend on the memory, or if the data is there in the cache, or it has to be loaded from the secondary memory. Okay, so only at that time we will get to know like what kind of delay. So accordingly, right, the instruction can be scheduled. But at runtime, but in compiler, we doesn't know where the data is going to be resided, whether it may be in cache or RAM or in secondary memory, we don't know. But during runtime, we may know. So where it may be there, at what rate the data is going to be come to the processor. So based upon that, it can do the schedule. Okay, so that's the advantage of dynamic scheduling. Okay, so these three cases that makes the dynamic scheduling more efficient than the static scheduling. The first, right, some dependence may not known at compiling time, so that can be handled. And the second one is, right, a code which is compiled for single pipeline can efficiently run on different pipeline, and it allows the processor to tolerate unpredictable delays, because during execution we will get to know like when the data is going to come. So based upon that, it may schedule it. So that is the third advantage of having the dynamic scheduling. So normally, right, when you just go with the pipelining, simple pipelining techniques, the major problem is in order instructions, issues, and executions. So whatever the instructions we are there, the instructions are issued in program order. So what I mean, assume that you have like this, like 1, 2, 3, 4. So if it is like this, so first this and then this. So right, it will maintain an order. So it will issue, the instructions are issued in program order. So suppose if any one of the instruction is stalled, suppose if it is waiting for in the pipelining, no later instruction can proceed. That's the problem with the simple pipelining. Okay, if any one instruction is stalled, automatically, right, the remaining instruction cannot proceed. So what they even sometimes this one, suppose we have like this. Okay, multiply some value like this, f1, f0, f2. Add f2 something, f1, f3, f2. Subtract some f4, f5, f6. Okay. We have multiple functional units. So what do you mean by that is, I mean if you take a floating point address, maybe, right, we may have multiple floating point address. So adder in the sense it is capable to do all the arithmetic operations. So assume that we have two floating point adders. Okay, so two floating point adder we have, and one mul we have. Let it be. So this line I'm just talking about this. We have multiple functional units. If suppose if your execution is in program, if it is in order, so if you look onto this instruction, the output of like this, output of mul is depending upon add. So what it has to be done? It has to wait. So thereby a stall will be there until it will execute. None of the things will get warped. But when you look onto this instruction subtract, is there any dependence between the previous instructions? Maybe, right, add is scheduled in this functional unit. Okay, add is scheduled in this functional unit. So we have one extra functional unit. Since since the instruction is executed in issued in program order, though this is capable to execute and even the functional unit is also available, but still in most of the cases it will be in idle case, because this is the long running instruction. If you take this, assume this may take 10, I think 24 clock cycles. Multiplication will take 24 clock cycles. After 24 clock cycles only add may get the result. After this only next subtract instruction has to get issued. So meanwhile, right, what we can do when the null is in execution here, what we can do? We can make the subtraction to be executed here. So that should be done here. That's what they're saying. So many functional units are available, but those units will also be idle when you are going for simple pipelining techniques. So we need to go for some alternate ways. Uh, yeah, here the same example this slide. So this is what I explained. See, division instructions, we have F0 and if this is dependent on this, but when you just take the this instructions, there is no dependence. So obviously, right, this can be executed, but when it is in order, the subd cannot execute. So definitely, right, this may leads to performance limitations. So what has to be done? The only procedure to be done is, right, we need to allow, that is we need to execute the sub.d, thereby we need to separate the issue process into two parts. This is important. Okay, so since we have multiple functional unit, if there is no data dependence, so probably, right, we need to execute that instructions. So when you are trying to execute, we need to we have to consider two things. One is what we have to check for any structural hazard, and we have to waiting for the absence of data hazard. So here, what is structural hazard? What is structural hazard? If with the example what I explained now, what it is checking, I need the sub function, the sub instructions to be executed. For that, I'm saying the issue process has to be divided into two parts. First, we need to check for any structural hazards. Here, what is structural hazards?
A resource maybe not be available, ma'am.
Which one,
like resource like adder or subtractor.
Yeah, right. Yes, exactly. Resource. Here, what is the resource we need? I told you, right? F adder. The previous slide, right? Because this is idle, but still we are not using it. So now we are checking, is there any resources available to execute this instruction? If it is available, probably, right, we have to go for this. At the same time, this is very important. Waiting for the absence of data hazard. If you have a true data dependence, probably, right, we need to wait. If we don't have, so we need to proceed. So that is the aim. So what actually what the outcome is, we need to still use the in order instruction, but we want the instruction to begin execution so as soon as the data operands are available. So we will go for in order instructions. Okay, when you are issuing, we will go for in order instructions. But what we are saying is, whenever the data operands are available, immediately we can execute the instructions. So obviously it results in what? It will go for out of order executions. So implying out of order completion. This what you take this, assume that this is going to be take 24 cycles, clock cycle. For example, I'm saying maybe this may take 12 clock cycles and this may take 12 clock cycles. So output of this is depend on this. Okay, when you are issuing, okay, your order in order we are issuing, so it is taking 24 clock cycles. So meanwhile, all the instructions can be issued by just checking whether the resource is available. If the resource is available, we can schedule these instructions. So thereby at 12 clock cycle, this instruction will be complete. You understood? Though we have issued the instruction in order, but what is leading? It's just going for out of order execution, because it is after 24 cycle only it will execute. But at when 12th cycles up, this will complete. So that's why they are saying, so when you're trying to do this, so it may leads to out of order executions, thereby implying out of order completion. Clear? So here we can go for in order instructions, but it may result in out of order execution or out of order completions. So what will be the problem when you are going for out of order executions? So definitely, right, out of order execution introduces the possibility of war and wow hazards. This is what I told you. Because keep remember, raw hazards we can't do anything, because it is holding the data operand what the instruction is needed, so that cannot be eliminated. We need to wait until it get the data. But when you just go for out of order executions, it may lead to the possibility of war and wow hazards. So what is that war and wow hazards? You take the sample examples. Okay, you take as make it fast. You find out how many true data dependence, how many anti-dependence, how many output dependence are there. Find out 5 minutes. I'll give a time. I'm just naming this instruction 1, instruction 2, 3. This is instruction 4. We find out like what are all the anti-dependence, what are all output dependence and true data dependence in these instructions. Okay, this is like consider as a toy program and try to do it. Found out. Okay, so true data dependence here in these instructions. How many true data dependencies is there?
2, ma'am.
Two. What are they?
I1 and I2 and I3 and I4.
I1 and I2. Okay, like output of this is going to be depend on this. So I think right, this is a data dependence between I1 and I2. You have a true data dependence. Another one is
I3 and I4.
I3 and I4. So it is writing and it is making use of this. So I3 and between I4, right, you have a true data dependence. Next, when you go for anti-dependence, I mean, true data dependence is what? Raw hazard, right? So when you go for anti-dependence, it is right after read. So between which two instructions you have?
I2 and I3.
Add and subtract.
Add and subtract, right? So here, right, we have what? F8. And here also, right, we have a F8. So what will happen? Suppose if you are trying to execute this instruction before this, so probably, right, it may lead to an error, but actually it is not dependence, isn't it? So this one, right, between instruction I2 and I3, you have this anti-dependence. Is there any case? I think no, right? Next, output dependence. What is output dependence? It is the wow hazard. Is there any wow hazard in this?
I2 and I4.
Huh? I2 and I4, right? So both here
Ma'am.
also is writing to F6 and here also, right, it is writing to F6. So between instruction I2 and the instruction I4, you have the wow hazards, but there is no data dependence, but both is trying to write to the same location. Suppose, right, assume in the later case, if suppose if you are going to read F6, what F6 should be? It should be the F6 from the multiplication only. It is not should be from add. So if suppose if you execute this before this, so here, right, it may result in wrong case. So that's what, right, I mean, these kind of things has to be avoided. I mean, probably it may, when you go for out of order executions, this one. Suppose since data, suppose we can execute this instruction before these two instructions. So, but here, right, we have this data anti-dependence and output dependence. So it may result in war and the wow hazards. So when you go for out of order execution, it clearly introduces the possibility of war and wow hazards. So we need to have one procedure to eliminate these things. Okay, I think this is what they are given. There is an anti-dependence between the add and sub. So this one, I mean, I given us instruction 2 and 3. So you have this. So if you execute the sub instruction before add instruction, it may lead to the war hazards. And the one more problem is imprecise exceptions. Normally, right, when you talk as an exceptions case, we have two things. One is the precise exception. The other one is the imprecise exceptions. So what is that is, normally, right, if suppose if we have a precise exceptions, we can reschedule it. I mean, which means we can go restore the things before exceptions and we can start continue. That we can say it as precise exceptions. Got it or not? So, I mean, we can, whatever the things that happened before exceptions, so till that we can do a restore. Before exceptions, we can restore and we can try to schedule the instructions and again, or and we can execute the program again. So that we can say it as precise. But when you just go with the imprecise exceptions, so you can't do anything. So it is the problem. I mean, which means, right, we cannot restore and obviously we cannot schedule it also. So when you just go for dynamically scheduled cases, so there is a possibility to generate the imprecise exceptions. So that has to be taken care properly. But this Thomas-Rawls algorithm is not dealing with it. The next topic we are going to see. So in that we will see how to handle these imprecise exceptions. So currently we will go with an assumption that there is no imprecise exceptions. So what is that is, here we have 2 points. The pipeline may have already completed instructions that are later in the program order than the instruction causing the exceptions. So I think an example, some simple example I'm explaining. You assume that we have this 4, 5, some instruction. In 8th instruction, don't think this is the data as that, just for conceptual aspects I'm explaining. Okay. So this case, right? Assume something I'm doing it, a divided by I. So these are all the instructions. Assume, I mean, before executing this instruction, 8th instruction is executed. So in this case, I value may be 0 now. When it is executing, so in the, maybe in ith instruction, first instruction, I value is 0. So this has been scheduled, and before that, this this instruction is going for execution. So don't think that this is data dependence. For example aspects I'm saying. So this is in case, but it is ready for execution. It is executed. Here, what has happened is a divided by 0. It leads to divide by 0 error. Okay, it leads to divide by 0 error. So, but maybe between these instruction I value, there is a possible for changing of I values. You understood or not? Since we just gone for executing, I mean, we gone for out of order executions, we have executed these instructions, but it may leads to the exceptions. But actually, it may not lead. If you executed in a proper mode, may not be. It may not leads to exceptions. Okay, this is one case. Or else the other case, suppose this is proper. Assume that this is like a by I. This is going to be proper. In this case, assume like I is 1, so it will be worked properly. But after executing this instruction, I value is 0. But what will happen? This has been executed before. But if you try to, actually this has to give an exception, isn't it? You got it what I'm saying? I will take this. Assume that we have these instructions 1, 2, 3, 4, so and so. 8th instruction is that. Okay, so something is there, some exception, some instruction it is there. Now we just assume that like a of I. So first instruction keep I as 0, first case. Okay. So 1 has been scheduled, maybe assume it has been executed. So now we know like I is 0. So later, right, this is in schedule now. Maybe it is depending on something. So now, right, this is start execution, start for executions. So this case, right, since it has been executed, it takes an assumption as a divided by 0. So what will happen? It may leads to exceptions. But actually, there is a possibility of changing I over here. After executing these instructions, there may be I value may be changed here. But since we have gone for out of order executions, we have resulted in an imprecise exception. This is one case. Another case is this case. So we have, currently assume that assume IS2 here. So based upon that, maybe this is executed, 8th instruction is executed. But 2, 3, 4, the output of I may be 0. But at that time, right here, it has to give the exceptions. But since we executed, we may not get the exceptions. But actually, right, this instruction is going to be, it should be an exception. So these are all the problem. This is the major problem with respect to the dynamic scheduling, which means when you just go for out of order executions, it may result in imprecise exceptions that has to be kept. They are just for a what to say. We have to go for the new hardware component. We have to introduce another new hardware component, and thereby we have to reduce this. So we will see this later. Okay. I mean, this was yeah. So this 2 point is trying to say this. Imprecise exception can occur because of two possibilities. One is right, the pipeline may have already completed instructions that are later in the program order than the instruction causing the exceptions. First case. The second one, the pipeline may not yet completed some instruction that are earlier in the program order than the instruction causing the exceptions. So now, right, it just you map both the what the example I explained with these two instructions. But this cannot be handled in this Tomas-Ros algorithm, but we will see later. Okay, so that's what they're saying. When you just go with the imprecise exception, it is made difficult to restart execution after an exceptions. That's the thing here. But in case of precise exceptions, we can able to restart. But in case of imprecise, it is very difficult to restart. So it has to be handled properly. Okay. So I mean, this is a base introduction. So when you just go for dynamic scheduling, so whatever the instructions, when it is at issue stage, it is going in order issues only. Okay. So however, right, whenever it waits for the operand, probably right, it needs to stall. So, but it will go for out of order execution. So we will have an in order issues, but we will go for out of order executions. So since we have an out of order executions, what we have to do is this stage, that is the ID stage, the instruction decode stage, has been divided into two stages. One is issue stage, another one is read operand. ID is divided into two. One is issue, another one is read operand. So what issue does is it will decode the instructions and it is checking for any structural hazard. So once it is decoded, it will get to know, right? What, because we have like this one, isn't it? 100111. So in the memory, it will be like this. So it will be decoded. It will decode and then it will find, okay, it is going to be whether it is an add instruction or sub or a multiply. Got it? So decode instruction does that, right? So once it knows, right, it is going to be add, sub or mul, thereby, right, it needs to check the corresponding functional units, whether we need an adder or multiplier or whatever it is. Okay. So that's why once it is decoded, it will check for any structural hazards and it will wait until no data hazards. That is very important, right? If suppose we have a here data hazard is true data dependence. So if you have a true data dependence, it has to wait until it reads the operand. So the dynamic scheduling, the name, right? It has been first developed by Tomas-Ros. So its approach, why it has been developed is, I think this is an IBM 360 architecture. So in that, right, we have only 4 double precision floating point registers. We discussed, right, when you go with the compiler, when you do a static scheduling, when you go for loop unrolling, what happened? What might be the problem in loop unrolling? Just we are unrolling, right? Is there any limitations for unrolling? Just like that we can unroll. You are online lurking la leda. What might be the problem in loop unrolling?
Size of code increases.
Okay, size of the code increases. Okay, that is a normal thing. Next.
More number of registers requirement.
Yeah, obviously that is a very important thing, right? We need more number of registers. Clear, but you just check about this architecture. How many architectures? How many registers it have? Only 4 double precision floating point registers. Understood. So clearly, right, with these 4 registers, we cannot go for the scheduling. So only this is the architecture that motivated, that leads to the dynamic scheduling. So that cannot be done by, which cannot be done by the compiler. So something has to be done. So, the Thomas-Lowe's approach has been designed for this architecture only, this IBM 360 architectures. Okay. So one is right, limitness in the compilers, registers, and another one is have long memory access. Sometimes, right, may have long time memory access or delays while performing the floating point operation. You may have a delay. So meantime, we can schedule some other instructions and we can do it. Okay. So these are all the major reasons why we gone for this dynamic scheduling. Okay. So what has to be done is this has to be minimized. It cannot be removed, but it has to be minimized. So what we need some mechanisms we have to track until the data operand is available. Immediately we need to go for execution. So that's the thing we have to do it. So that's all. The raw hazards are avoided by executing an instruction only when the operands are available. It's quite natural, right? Because raw hazard is a true data dependence. Only when the operands are available, then only, right, we need to go for executions. So now, right, we are just going to introduce the register renaming. Thereby, we are trying to reduce the var and bob hazards. So this one, with the help of the Thomas-Lowe's approach, just we are going for register renaming. So which means we are not going to use the physical registers like R0, R1 or F0, F1. We are not going to use that. So somewhere we are going for register renaming. Thereby, right, we are trying to minimize the var and the bob hazards. So, I think, okay, the same example. I think this is what we are seeing, right? How many, the same for the same instructions. I think one more instruction has been added here. So for these instructions, how many anti-dependence, how many output dependence, true data dependence. We just kindly go through now, 2 minutes. Else we'll take this. If you take like this, we take like I1, I2, I3, I4, and I5. First, we will go for true data dependence. So since it is depending on this, okay. So between I1 and I2, we have a data dependence. Next, and F8, right? So this is depend on this. So between the instruction I4 and I5, we have a data dependence. Next, add and this one, right? Whatever it is adding, it is trying to store here. So probably, right, this part. So this is going to be the other data dependence between I2 and I3. Next, anti-dependence. Anti-dependence is between add and the sub. So in this part, right? So F8, the similar examples, I think. So F8. So this part is the var hazards, right? Between add and sub, between instruction I2 and the I4, we have this anti-dependence. Similarly, right, store and mul. Where is store and mul? Here, why it is anti-dependence? Is it anti-dependence between store and mul?
Output dependence.
It is output dependence. Is it
Output dependent. Output dependent.
Output dependence? I know you people will say like this. See, when you go with the store instruction, keep remember this is the source operand and this is the destination operand. Think like this. Got it? Rest of the cases, if it is mul.d, this is destination operand, these are all the other two operands. Understood? So if it is a destination operand, then right, when it will be destination, only if it is load, then this is going to be a destination operand. Here it is a store operand. So whatever the data in this is going to be stored over here. Got it or not? So that's why, right, this instruction has been clearly given as anti-dependence. Okay, what is var, right? Right after read. So this is read. We are reading the data from M6 and from M6 and it is moving to the position, to the location R1. Got it or not? We are reading and just moving to here, right? We are trying to write, right? It comes under wow hazard. So this you have to be very careful when you just go with the store instructions. So don't interpret this as the destination and don't write it as out dependence. This is anti-dependence. Clear? Any doubt in this between I3 and I5? Guys, any doubt?
Yes, ma'am.
Clear, okay. And what is the output dependence between the instruction add and mul? Okay, this one, right? Between here and here. So this is going to be the output dependence between I2 and I5. I think the similar example, only thing is we have added the store instructions. So thereby this has been introduced. Okay, so I think this, you people will do the mistakes frequently. So try to do it. Clear? I think these are all the dependencies that is available in this code, right? So the true dependence are output dependence and the anti-dependencies. So what we can do is these three things cannot be eliminated. So since it is a true data dependence, clearly, right, it cannot be eliminated. But these three things, this and this, can be eliminated because those are all what only var and the wow hazards. So clearly this can be eliminated. So how it can be eliminated? So the only thing is, right, we need to go for register renaming. So how to do the register renaming? So here, right, they used, assume they gone for some temporary registers. Here, where are the places? I2, I4. Okay, this is I1, I2, I3, I4, and I5. Okay, so between this, what and what? Wait. Okay, so here, right, we had the previous, here we have, okay, so here, right, we have the instruction F8, F8, but there is no data dependence, only the name of the register is same, but it gives us a illusion there is a data dependence. So what we need to do is, so we have to rename it. So this F8 has been renamed as T. Okay, here, right, the F8 has been renamed as T. And keep remember, wherever you are using after that, all has to be changed. So that is very, very important. Clear? So we have to change it out. And next we saw this output dependence. Output dependence, here we have F6 and here also, right, we had F6. So instead, right, what we are doing is just they are changing this to yes. So this one. So they are changing yes and this also has been changed to yes. So because of this, what is happening? This wow hazard is also is not available, isn't it? We just check these instructions now. Just find out is there any wow and wow hazard is there. Just they did these two renaming instead of those two registers. They given new name. Don't think this is the physical registers. Just for understanding, they changed it. That's it. They changed it to S and T. So is there any war and wow hazard in this code? Anything is existing still? True data dependence, we cannot do anything. Only we have to worry with anti-dependence and output dependence. So to eliminate anti-dependence and output dependence, we need to go for register renaming. That's all. This is the today's outcome also. You should know. So how to avoid war and wow hazard? It can be done with the help of register renaming. Here, just like that we did, but there is some procedure to do it. Just for an illustration aspects, this has been given. Okay, so normally, right, the register renaming can be done by the compiler, but But when you just go, as I told you, right, within basic blocks, it can be easy to schedule it. But when you are just going for multiple blocks, so commonly it may be